In this video, I will discuss the concepts of heat and phase changes. These ideas should be a review from your previous chemistry course. Heat is often a term that is used inconsistently and usually is confused with temperature. Heat and temperature are not the same thing. There is a very clear distinction between the two. You may commonly speak of the flow of heat. Heat flows from the sun to the earth and from a stove burner to a pot. Heat flows spontaneously from one object to another because of a temperature difference. In the 18th century, heat flow was believed to be due to a fluid substance called caloric. So this fluid, caloric, would flow from the hotter object to the colder object. But through experimentation, the caloric fluid was never able to be detected. Heat is not actually a substance. In the early 1800s, an English brewer, James Prescott Joule, pursued the idea of heat further. He believed that heat was related to energy or work. His experiment, which proved this theory, is shown. The falling weight causes the paddle wheel to turn. The mechanical equivalent of heat describes the relationship between heat and work that was discovered by Joule. Quantitatively, 4.186 joules of work was found to be equivalent to 1 calorie of heat. 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Also, 4,186 joules equals 1 kilocalorie. 1 kilocalorie is the amount of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius. As a result of Joule's and other experiments, scientists now interpret heat not as a substance and not as energy, but as a transfer of energy from one object to another because of a difference in temperature. The SI unit for heat is a joule, although calories and kilocalories are still sometimes used. Joule's result was crucial because it extended the work-energy principle to include processes involving heat. It also led to the establishment of the law of conservation of energy. Temperature, heat, and internal energy are often used interchangeably, but as we have seen, temperature and heat are very different concepts. There is also a very clear distinction between heat and internal energy as well. Internal energy is defined as the sum total of all energy of all the molecules, objects, including chemical or electrical potential energy associated with the chemical bonds between the atoms and the molecules, nuclear energy, and thermal energy. We will ignore the chemical and nuclear energy and concentrate solely on the thermal energy, which is defined as the part of the internal energy that results in temperature. It is a measure of the average kinetic energy of all the particles. Internal energy, U, is calculated by taking the average kinetic energy of all the molecules and multiplying it by n, the number of molecules. But recall that kinetic energy is equal to 1/2 mv squared, or is also equal to 3/2 kT. plugging in 3 halves kT for kinetic energy, or Ke, we get U is equal to 3 halves nkt, or sometimes a useful equation is delta U equals 3 halves nk delta T. These two are very useful formulas, but because nk is equal to nr, where in this case the n is number of moles, we can replace capital NK with lowercase n r, and we have a new set of useful equations. U equals 3 halves lowercase n rt, or delta U equals 3 halves lowercase n r delta T. Thus, the internal energy of a gas depends only on the temperature and the number of molecules, or number of moles. The second set of equations are more often used, but the first two are important as well. In summary, temperature is defined as a measure of the average kinetic energy of all the molecules. Heat is the transfer of energy from one object to another. And internal energy is the sum total energy of all the molecules, which is the average kinetic energy multiplied by the number of molecules. If heat flows into an object, the temperature rises. But how much does the temperature rise? That depends. Obviously, the more heat you add to an object, the more the temperature will change. But what about the size of the object you're heating up? If a small amount of heat flows into a cup of water versus a large body of water, the cup of water will change temperature more because it has less mass. Lastly, what if we compare the cup of water to a small piece of iron? Because the materials are different, they will change temperature at different rates. This quantity, called specific heat, is a characteristic of the type of material. The higher the value of the specific heat, the harder it is for the object to change its temperature. These values can be found on page 387 in your textbook. So the change in temperature of a material is proportional to the amount of heat added and inversely proportional to the mass and the specific heat. So the more heat, the more the change in temperature. The more mass, the smaller the temperature change. And the greater the specific heat, the smaller the temperature change as well. Or this can be rearranged to show that the amount of heat required to change the temperature is dependent upon the mass, the specific heat, and the change in temperature. Q, the heat, is equal to mc delta T. You may be wondering what units specific heat is measured in. If we rearrange the equation to solve for C, the specific heat, we get C equals Q over m delta T. Q, heat, is measured in joules. M, mass, is in kilograms. And delta T, the change in temperature, is measured in degrees Celsius. So the units are joules per kilogram degrees Celsius. Sometimes calorie per gram degrees Celsius are used as well, but less frequently than the first. Values using both units are shown on page 387. Let's take a look at our first problem. Through how many degrees Celsius does the temperature of water going over a waterfall of a height of 20 meters rise? Assume that all the mechanical energy is converted into heat. So in this problem, we are defining the mechanical equivalent of heat. We are saying the initial mechanical energy is equal to the final amount of heat. This is basically a statement of law of conservation of energy. Recall from our energy unit, the mechanical energy is equal to the sum of kinetic and potential energy. But we're going to assume that the water is not moving at the top of the waterfall because we weren't given a speed. So the water only possesses potential energy, which can be calculated using the formula mgh. Setting mgh equal to Q, which is mc delta T, we can then plug into the equation. However, you may have noticed that we were not given a mass, but not to worry, because mass is found in both equations and thus cancels out. So we only need GH and C, which we do have. So plugging in our given values and solving for delta T, we find the temperature change to be 0.05 degrees Celsius. Not a huge change in temperature, but again, this defines the mechanical equivalent of heat. The mechanical energy is converted to heat and results in a change in temperature. Problem 2. A lead bullet is moving with a speed of 200 meters per second and pierces the ground. What is the temperature change if 50% of the kinetic energy is converted into heat? Specific heat of lead is 130 joules per kilogram degrees Celsius. Pause the video for time to work on the solution. So the bullet begins with kinetic energy, which can be calculated using 1/2 mv squared. The kinetic energy is converted to heat, Q, which is mc delta T. So normally, we could set the kinetic energy equal to Q, the heat, if all of the kinetic energy is converted to heat. However, in this problem, we're told that only 50% of the kinetic energy is converted to heat. So we have to take the kinetic energy and multiply it by 50%, or 0.5. So we'll set the equations for Ke and Q equal to each other, and multiply the Ke by 0.5. We can plug in the equation for kinetic energy and the equation for heat. And again, we encounter a problem where we are not given the mass, but because it's present on both sides of our equation, it cancels, and we can plug in all other values. Solving for delta T, we get 77 degrees Celsius. Problem 3. How much heat input is needed to raise the temperature of an empty 30 kilogram vat made of iron from 15 degrees Celsius to 100 degrees Celsius? And what if the vat is filled with 30 kilograms of water? Pause the video for time to work on the solution. First, we want to find the amount of heat required to change the temperature of the vat. So, Q is equal to mc delta T. We have mass. Specific heat is in your textbook. And the change in temperature is from 15 degrees Celsius to 100 degrees Celsius. So delta T is T final minus T initial, or 100 degrees Celsius minus 15 degrees Celsius. And so for Q, we get 1,147,500 joules. B says we are now considering the vat filled with 30 kilograms of water. So now when we add heat, it will change the temperature of the vat and the water. So we'll find the amount of heat required to change just the water from 15 degrees Celsius to 100 degrees Celsius. So Q equals C delta T, plugging in the mass of the water, the specific heat of the water, and the change in temperature, again, final minus initial. We find the heat required to be 10,675,300 joules. It requires much more heat to change the temperature of the water by the same amount because it has a higher specific heat than the vat. But because we're asked for the total heat required to change the temperature of the water and the vat in part B, we have to add the two heat values together and we get 11,821,800 joules total. Specific heats for gases are more complicated than for solids and liquids. When gases change temperature, both pressure and volume can change. The specific heat of a gas depends on how the process is carried out. Most commonly, we deal with the specific heats of gases kept at a constant pressure, C sub P, or a constant volume, C sub V. Some values are given on page 388 of your textbook. The equation used to calculate heat is unchanged, but the specific heat value that we plug into the equation depends on the type of process. So Q equals mc delta T, but C, the specific heat in the equation, is either the CV value or the CP value, depending on how the process was carried out. You may also notice on page 388 of your textbook that CP is always greater than CV. It can be further derived that CP is equal to 5/2 R, where R is the universal gas constant, and CV is equal to 3/2 R, again R being the universal gas constant, for ideal monatomic gases. So again, CP is always greater than CV. You will not memorize those last equations, but they are sometimes useful in problem solving. These equations will be given to you in a problem if it's necessary to use them. In discussing heat and thermodynamics, we shall often refer to particular systems, which we call calorimeters. A system is a set of objects we wish to consider. Everything else is known as the environment or the surroundings. We will often study isolated systems, in which no energy enters or leaves the system. For example, consider a container filled with water at room temperature. A hot cube of iron is placed into the isolated container. What happens? Because there's a difference in temperature, heat will leave the iron. But because this is an isolated container, the heat cannot be lost to the environment, so all of the energy or heat is transferred to the water. So heat flows from the iron to the water, obeying the law of conservation of energy. In other words, the energy out of one part of the system, the iron, is equal to the energy into another part of the system, the water, or heat lost equals heat gained. We can plug in mc delta T for Q, but how do we deal with the lost versus gained? We can negate one side of the equation. By convention, we negate the side where heat is lost, but it really doesn't matter. In all examples and problems of this sort, be sure to include all objects that gain or lose heat. If we have multiple objects losing heat, then we must incorporate another mc delta T on the lost side for that second object. And if we have multiple objects gaining heat, we must incorporate another mc delta T on the gained side. Problem 4. An aluminum can with a mass of 0.5 kilograms contains 0.13 kilograms of water at a temperature of 20 degrees Celsius. A 0.2 kilogram block of iron at 75 degrees Celsius is dropped into the can of water. Find the final temperature of all 3 objects, assuming no heat loss to the surroundings. Pause the video for time to work on the solution. Again, it's important to note that we are finding the final temperature of 3 objects, not just 2. To begin, we set heat gained equal to heat lost, and use mc delta T for each object. The water is gaining, and the aluminum is gaining heat. So we have 2 mc delta T's on the gained side, one being for water, the other being for the aluminum. And the iron is losing heat, so we have the mc delta T for iron on the other side of the equation. But we also negate the lost side, plugging in values and performing simple algebra. We will get the final temperature to be 24.6 degrees Celsius. As we mentioned before, when heat is added to an object, it changes temperature. However, this is not the case when an object is undergoing a change of phase. For example, let us trace what happens when a 1 kilogram block of ice at negative 40 degrees Celsius is heated at a slow, steady rate until all the ice changes to water and then is changed to steam above 100 degrees Celsius. So we'll begin with the ice at negative 40 degrees Celsius, below the melting point and freezing point. As shown in the graph, the temperature of the ice rises as heat is added. However, when 0 degrees Celsius has been reached, the melting point, the temperature stops increasing, even though heat is still being added. This is because the heat or energy goes into changing the phase, not the temperature. Thus, the ice gradually changes to water in the liquid state, and there's no change in temperature. Once fully melted, continued addition of heat causes the water's temperature to increase. When 100 degrees Celsius has been reached, the boiling point, the temperature stops increasing again, even though heat is still being added. This is because the heat or energy goes into changing the phase and not the temperature. Thus, the water gradually changes to steam or begins to boil. Once all the liquid has changed, the temperature then begins to rise again with further addition of heat. It is important to note that if we're going the opposite direction, from steam to water to ice, heat must be lost, and the Q's would be negative. To determine how much heat is added, we can break the graph into segments. We will begin concentrating on those sections of the graph where temperature is changing. For the first segment of the graph, we use mc delta T to find the amount of heat added for a given change in temperature. At times, though, you will only use a small part of the segment, so be sure to choose the correct initial and final temperatures. For the next segment of the graph, we will again use mc delta T. In this case, the liquid is changing from 0 degrees Celsius to 100 degrees Celsius, so we use the entire segment. But in some problems, only a portion of the segment will be used. Again, be sure to choose the correct initial and final temperatures indicated in your specific problem. For the last segment of the graph, we use mc delta T to find the amount of heat added for a given change in temperature. In this case, the gas is increasing temperature from 100 degrees Celsius, the boiling point, to a higher temperature. At times, you will only use a small part of the segment, so be sure to choose the correct initial and final temperature. So what about the other segments of the graph? Let's take a look at the first horizontal segment of the graph. Heat is being added, but the temperature remains the same. This is because the substance is undergoing a change in phase from solid to liquid or liquid to solid. Again, there's no change in temperature, so mc delta T cannot be used. Delta T would be 0, so Q would be 0, but we know that the heat is not equal to 0. So instead, we must use the formula Q equals m sub F, where m is mass and L sub F is the latent heat of fusion, which indicates what kind of material is undergoing the phase change. The higher the latent heat of fusion, the more heat is required to change the phase. The values for latent heat of fusion for common materials are given on page 392 in your textbook. So what's the difference between melting and freezing? We denote a gain in heat as a positive Q, and this case would be considered melting. If heat is lost or released, it is denoted as a minus Q, which would mean freezing. For the second horizontal segment of the graph, heat is being added, but the temperature still remains the same. This is because the substance is undergoing a change in phase, but this time from liquid to gas or gas to liquid. Again, there's no change in temperature, so mc delta T cannot be used. Instead, we use the formula Q equals m times L sub V, where m is mass, and L sub V is the latent heat of vaporization, which indicates what kind of material is undergoing this change. The higher the latent heat of vaporization, the more heat is required to change the phase. The values for latent heat of vaporization for common materials are also given on page 392 in your textbook. We denote a gain in heat as positive Q, and in this case would be considered vaporization. And if heat is lost or released, it is noted as a minus Q, which would mean condensing. Problem 5. How much energy does a freezer have to remove from 0.5 kilograms of water at 20 degrees Celsius to make ice at negative 6 degrees Celsius? If we look at the graph, we are going from liquid water at 20 degrees Celsius to ice at negative 6 degrees Celsius. For the first segment, the water starts at 20 degrees and loses heat until the water reaches the freeze point at 0 degrees Celsius. Note we are not using the entire segment from the boiling point to the freezing point. So for this part of the graph, we must use mc delta T for the water decreasing temperature from 20 degrees to 0 degrees Celsius. Because the temperature is decreasing, we will get a negative Q, which means heat is being lost. For the second segment, the water is undergoing phase change, which is freezing, or liquid to solid. We cannot use mc delta T because there is no change in temperature, so we must use Q equals mass times the latent heat of fusion. But because the water is freezing, heat must be lost, and if we use mass times the latent heat of fusion, it doesn't give us a negative number. So we have to throw in that negative for mass times latent fusion to denote that heat is actually being lost. And for the final segment of the graph, the ice is decreasing temperature from 0 degrees Celsius, the freezing point, to negative 6 degrees Celsius, so again, we'll use mc delta T. This will give us a negative value for heat because the temperature is decreasing. To find the total amount of heat, we must take the sum of all the values. Plugging into the equation, we have mc delta T for water, which is going to give us a value, plus mass times the latent heat of fusion, but even though we're adding that, it comes out to be a negative value because heat's being lost, so we have to throw the negative in for that. And then adding to that the MC delta T for ice going from 0 degrees Celsius to negative 6 degrees Celsius. And we find the total heat to be negative 214,660 joules. And it comes out to be negative, meaning that heat is lost or released. Problem 6. A 3 kilogram block of iron was taken from a furnace where its temperature was 700 degrees Celsius and placed on a large block of ice at 0 degrees Celsius. The ice melted and the final temperature of the system was 40 degrees Celsius. Assuming that all the heat given up by the iron was used to melt the ice and heat the water, how much ice was melted? Pause the video for time to work on the solution. So heat lost by one object is gained by the other. So we have MC delta T lost by the object, and we put in the negative to show that it is, in fact, heat lost. And that's going to be equal to the heat gained by the ice. But not only is the ice melting, but the water, once it's melted, is increasing to a temperature of 40 degrees Celsius. So we have to include both mass times the latent heat of fusion and MC delta T for the ice and water. Plugging in our values, on the right side of the equation, we'll be left with an M times the latent heat of fusion and an M times C delta T. Doing a little bit of algebra to things up a bit. For the first term, for the heat lost, we get 891,000 and set that equal to mass times the latent heat of fusion, which is 333,000. And then MC delta T, we get the mass times 167,440. Adding the two M terms together, we get 500,440. M is equal to 891,000. And dividing both sides by 500,440, we get the mass to be 1.78 kilograms. So 1.78 kilograms of the ice has melted and increased its temperature to 40 degrees Celsius. Problem 7, our final problem. A 70-gram bullet traveling at 250 meters per second penetrates a block of ice at 0 degrees Celsius and comes to rest within the ice. Assuming that the temperature of the bullet doesn't change appreciably, how much ice is melted as a result of the collision? And be sure to know that it's just melting, not actually increasing its temperature too. Pause the video for time to work on the solution. So the bullet is beginning with kinetic energy, which is equal to 1/2 mv squared. We can find the amount of kinetic energy the bullet has by plugging in the mass and the speed to get 2,187.5 joules for our kinetic energy. Because the bullet is coming to a stop within the ice, then all of the kinetic energy must be turned into another form of energy, in this case, heat. So the kinetic energy is equal to the heat, which is 2,187.5 joules. Now that heat is being put into the ice, or transferred to the ice, to solely melt it. And when we have a phase change, in this case from solid to liquid, we use Q equals mass times the latent heat of fusion for the ice or the water. So plugging in our Q value, which is equal to the kinetic energy, and setting that equal to the mass times the latent heat of fusion, which is 333,000 joules per kilogram, we find the mass to be 0.007 kilograms.